Yes, it is visible.
Okay, then that's great. Okay, then let's start. Actually, I am having two sessions, as I said, and as you know already. And in these two sessions, we'll try to discuss the operational amplifier. And most importantly, I would like to establish a fair amount of stage so that you can go further and do. Uh, I believe that you can do little bit research about the operational amplifier and hope it will be publishable. So, and more importantly, I'll assume that you are having little bit or at least basic knowledge about the analog circuit as well as some operational amplifiers topology so that I can build up for that. Even though if you don't know, it's not a matter because I'll cover up that as well. But I'll go quickly through that. So because as time is limited, I have to rush through the slides sometimes. If anybody is having the doubt or concern or queries, he can uh, you can ping me at that particular amount of time or later of the presentation. For the reference, you can mention the slide number, which I have mentioned at the right of the bottom. Right of the bottom. Okay. Before proceeding ahead, also I would like to give one disclaimer because I'm not nowadays in a teaching fraternity, and I'm not having that much experience as or you are having according to teaching. So I may slip somewhere so that just for a caution, hopefully you will understand the concern which I'm raising. Thank you. Okay, with this, we'll start. What we are going to see today, little bit fundamentals about the operational amplifiers. High gain is very important considering the accuracy. Uh, After that, we'll go for a low noise op amp.
Dr.
Uh,
Vinayak, we
the,
are not able to see your presentation. We are seeing only the what you say Microsoft PowerPoint window, not the slideshow.
oh, okay. Uh,
So,
1 second. Is it visible now?
not yet. Yeah,
Okay, let
yes,
me.
yes, it's visible, but the presentation, yes.
Mm, is it
But once
okay
you put in
or
no, but once you put in slideshow, we are still seeing the PowerPoint window, not the slideshow. Now it is fine. Now it is fine.
now it's fine?
Yes,
Now
yes,
the slide number 2, table of contents.
yes. Correct, correct. Yes, thank you.
Okay, okay, then no problem. Hope everybody is having on the same page. Okay, I guess nobody replies, so that I believe that everybody is on the same page. Okay, then what we are going to see, we'll quickly go through the basic of op amps, right? And before proceeding ahead, again, operational amplifier I'll consider as a, I'll not make that much difference between OT and op amp. Now, what principally difference between the OT and op amp is generally OT is having the high output impedance node compared to the operational amplifier, right? Because operational amplifier is OT plus buffer, we call it as operational amplifier, right? But here, generally, in other books or other papers which I came across, what we are saying is that generally transconductance amplifier, which people are using for filter design and all, they'll call as a OTA. And in general, even though circuit is having the high output impedance node, people are calling as op amp, right? That subtle difference it is there. Means here, even though if in this whole presentation, even though if I'm calling it as an op amp, it is a circuit of high output impedance node, right? Means I'm not considering I have connected the buffer at the output of the uh, high impedance node, right? So that after that we'll see the high gain. High gain is very much concerning nowadays because as the technology reduces, the intrinsic gain of the MOSFET itself is reducing significantly, so that getting the high gain is very, very difficult. Apart from that, why high gain is important? Because high gain gives accuracy, uh, nowadays designing a very accurate circuit at a lower technology node, it's really a critical job to do, right? Apart from that, noise is one of the concern which everybody talks about, whether it is a uh, high frequency application or a low frequency application, because low frequency application generally are limited with the flicker noise. If you go for a high frequency, you are limited by the thermal noise, right? So that while designing a operational amplifier, again we have to consider the noise as a uh, a prime specification. Apart from that, high speed op amp, and generally it is a conception that if I pump the larger amount of current, I can get the as much as speed I can get it out of that circuit. But generally it is not true, because you are getting limited by the other non-dominant factor as well, because the moment you started pumping the larger amount of current, other factors will also come in, so that you'll get the higher speed at the consuming power. But that is not all the way it is true, because other factors will come into the picture, and it will have some set limit before that you cannot proceed ahead, right? Then we'll see the two-stage amplifier. After that, we'll do some comparisons, whatever architectures we have seen. Uh, then we'll come to the current topics which people are really struggling with nowadays. That's the low voltage amplifier, because nowadays VDD is limited to 1 volt, and it may fall down further. So that designing a high swing amplifier, high gain amplifier, low noise amplifier is it's really difficult task, so to say. So that how people are solving those issues, that we'll see within this heading. After that, we'll go through the three-stage amplifier, and at the end, I'll take the case study where we have designed and published one of the operational amplifier, and we'll see the details of that, right? Then this is the first slide number 3, that is basic of op amp. This is nothing but like hopefully I have changed the slide. Everybody is seeing the slide number 3, I guess. Dr.
Yes,
Naveen?
yes, it's slide number 3.
Okay. Then we'll see the basics of op amp. This picture, it's very, very familiar with everybody, those who works on similar domain. And this is nothing but adder, right? And adder equation is having some amplification factor, that is RF by R1, RF by R2, RF by R3, depending on the whatever amplification you needed across every voltage, right? But the equation which we have studied into the book, it is having huge assumptions behind that, right? First assumption is that voltage gain is very, very high, right? Because if voltage gain is very, very high, then only I can write this kind of simplified expressions. Otherwise, it is not possible, because closed loop gain, if you remember the equation, closed loop gain is equal to open loop gain 1 plus beta into open loop gain, right? Then this equation, which you can see at the right hand side, is only valid when your operational amplifier is having the very, very high open loop gain, right? And generally, if using the 741, it is easily we can get a very, very high gain, right? But again, that is pre-assumption that it is operating at a very, very low frequency, right? If I remember correctly, 741 having the UGB of 1 megahertz, right? But, okay, then you can guess that how much open loop gain at the low frequency it must be giving, right? Second, that input current is equal to 0. Input current is equal to 0 is not having problem nowadays, because unless and until we are going for a very, very high frequency where input transistor is the BJT, right? Uh, we don't have to worry about the input current is equal to 0, because nowadays all the transistors majorly is input transistor is a input differential pair is a MOSFET, so that we don't have to worry much about that, right? But nowadays, yeah, really it is going to be a concern because emerging field like photonic ICs, as well as very, very high frequency circuits for 6G, or particularly 6G, we can say, people are going for a BJT, right? Because BJT is having the uh, exponential relationship between the voltage and current, right? So that uh, so that we'll get the again we'll get the very, very high speed, but again you have to lose the uh, input impedance, right? Because as input current is zero, that means it is having the high input impedance. And MOSFET gives, for time being, we can say that I'm using the MOSFET so that I don't have to worry about. After that, differential input voltage is zero. Again, differential input voltage is zero only when your operational amplifier open loop gain is very, very high. Bandwidth is high, and gain bandwidth is again very, very high. It should be. Means this simplified expression is having a lot of unsaid things, which generally we neglect. But when you go for a real IC design, we have to consider all those things into our mind and proceed further, right? Again, this is this these three circuits is the three circuits are really basics, but this gives a lot of insight about the analog IC design. That's why I put this slide into here, because every circuit tells a different story altogether, right? If you see the left-hand circuit, it is nothing but an inverting amplifier. It gives the uh, gain of closed loop gain of R2 by R1, right? With the sign of inversion, that is a minus. But unfortunately, what analog IC design always thinks about, you will not get anything for the free, right? So that here you'll get the inversion, but at the cost of reducing input impedance, so that you can see that input impedance is only R1, right? And extreme right, you can see that mm, it is nothing but a buffer, right? AV is equal to 1. But and here you are losing the gain, but what you are gaining is what you are achieving is Rin is infinity, and more importantly, which is not mentioned over here, R out is 0, right? So that we can call it as a buffer, right? And middle circuit is kind of optimum. You will get the gain is 1 plus R2 by R1, no inversion, but you will get the Rin is equal to infinity. Then I'll ask question, or you can go back and do some hand calculations. What will be the output impedance for first two circuits, means middle circuit and left hand circuit? That you can figure it out. I don't think so. It is very, very difficult, but still you can say that whose output impedance is having the higher value than the other, right? This you can do at the exercise. Then we are moving to the slide number 5. This is a simple frequency response of a operational amplifier, right? And A0 is nothing but a low frequency open loop gain, or open loop gain, which generally will get at the lower frequency only, unless and until it is filters or something, right? And at the first our dominant pole, which is at F1, we are getting the phase difference of 45 degrees, right? And asymptotically, it will reach to 90 degree. I'm saying that asymptotically it reached to 90 degree. That is really, it means like that, because the moment you started simulating this operational amplifier, you will not reach minus 90 degree at any point of time, even though if you increase the frequency. That you will get only when your frequency is infinity, right? So that just you can try it. You might have tried also that you will get 89.999, but never 90 as the frequency increases. And as you can see that this is also very fundamental. As you can see that this is only one dominant pole it is having, so that we can say that if system is having only one dominant pole, then it is inherently stable. So that we can see over here at the GBW, we are having the phase margin of 90 degree. 90-degree phase margin is very, very good, so that you don't have to worry about the stability at all, right? So that generally people will prefer the single pole system. But single pole system, which is dominant pole system, again I can say, single pole system uh, is comparatively easy to design, but again, it is having some demerits as well. Uh, but still, people would like to design the uh, dominant pole system, right? Always they'll try to make their system look like a dominant pole system, so that phase margin is relatively higher, so that you will get the very good stable system, right? Whatever response we are seeing over here is an open loop response. The moment you have uh, started closing the loop, you will get the closed loop gain, right? And closed loop frequency response. You can clearly see that at AC, that is green plot. You can say that you have reduced the gain, but you are increasing the frequency, right? That is the 3 dB frequency has increased. And always the moment you started from green to blue, your 3 dB frequency increases, uh, but your loop gain started reducing, right? And you can say that gain bandwidth product for all three will be same. In fact, all four, because at red we are connecting that operational amplifier into unity gain configuration, so that you'll get the gain 1, but operating frequency is very, very huge. That is uh, maximum bandwidth you can get out of that, right? And one interesting fact is that if you uh, if you take the integration of that particular area is always equal for everything, right? That is A0 F1 is equal to AC F1C and AC is equal to F1C, right? So that all this system is kind of a stable system and having the phase margin approximately 90 degrees. So that we can say that this is the operational amplifier when we are, how this operational amplifier works when we are connecting into the open loop or in a closed loop, right? Apart from that, there are some basics of op-amp, right? And as I said that generally people like designer like the single pole system, because single pole system is kind of a dominant pole system, the slide which we have seen just now, because it gives the phase margin very, very high, a very, very high value, and it will help to get the achieve the stability, right? So that if the left hand side, which we are seeing as operational amplifier, it is a single pole amplifier. At the output pole is very high, means output pole is at very low frequency, as R out is very, very high. And this is generally uh, cascode circuit, right? Or cascode amplifier, a single stage extension of a CS amplifier apart, and it is having only one dominant pole. And wide band amplifier, it is having multiple poles uh, at the different frequencies, so that you can operate at the wide frequency range. But generally we'll concentrate in this presentation only for a working of a operational amplifier, right? And this is one of the application of op-amp, and generally this we are using for designing a filter, particularly this application says. And if I'm using the different switches to connect the different value of capacitor, depending upon the value of capacitor, we'll get a different low pass filter. It's nothing but the integration, so that if I'm using the RC, we are having the uh, errors which is lesser than 20%. So that and generally these RC filters along with the op-amp is quite helpful to get the low noise operation or low distortion operation, but at the cost of heavy process variation, because R and C both changes with the process sorry, quite significantly, right? So that this is one of the application, uh, and this circuit is called as active RC filter, right? And this is the just a comparison uh, for for just information. That is for RC. If I'm using the active RC filter, you will get the very good gain bandwidth. I mean, it's very high low frequency gain, but you will not get the uh, but and apart from that, distortion and tuning ratio is very high. The moment you are coming to the switch capacitor kind of active filter designing, means you are replacing your R with the C, right? And that switch R with the C and some switches, and you'll operate those switches with the different frequencies so that you'll emulate the uh, R using switches and C, and it is having a comparatively higher distortion, so that which you can see very clearly over here. So that this is just this slide is just for reference. Okay, now we'll come to the real problem which people are facing nowadays. That is, nanometer CMOS technologies are leading to a smaller channel length along with the supply voltage below or equal to 1 volt. Now, whatever technology which I have worked, it is VDDs, maximum VDD permissible is 1 volt or 1.1 volt, depending upon foundry, it varies, but generally we can stick to the 1 volt. Right, and this slide is quite interesting. At x axis we can see that technology node, and y axis we can see the how much gain you can get, right? And that blue buildings are quite high, you can say, till the technology node is 65 nanometer, and red buildings are quite small, right? And red is representing the uh, digital MOSFETs, and blue buildings are representing, or blue chart is representing the analog MOSFET or RF MOSFET, right? And at 65, 45, and 30, it is quite interesting to see that, because in 65, you can see that analog, if I'm designing the operational amplifier using the analog MOSFET, you are having very high gain. Somebody has asked a question. 1 second. Okay. Okay. Sorry. Then analog MOSFET having the higher gain, as if I'm realizing those circuit or operational amplifier with the digital CMOS, then I'm getting the lower gain in 65 nanometer. 45 nanometer is almost similar, and surprisingly in 32 nanometer onwards, we can say, you are saying that if I'm realizing the operational amplifier with the digital MOSFET, I'm getting the higher gain compared to the analog MOSFET, right? Or analog process, we can say. Why it is happening? That is really a point of intention, right? Why it is happening is, if I'm in particular 32 nanometer technology, if I'm using the digital CMOS process to realize the operational amplifier, I'll get the higher gain, because in analog process of that 32 nanometer technology, it is having some more mass. Because of that, you are having the higher VTH and a higher threshold voltage of that particular analog MOSFET, so that your GM will reduce further and you will get the lesser gain. And digital, you are not having that much mass to reprogram or tune the threshold voltage, so that you are getting the higher VTH, so that you can get the higher gain. That is precisely the reason, as the technology node reduces, and digital CMOS operational amplifier will give the higher gain compared to the analog based CMOS amplifier or analog process CMOS amplifier. But still people are not preferring digital process to design analog blocks, because because as I said, as for analog MOSFET, we are having some different mask or additional mask for a threshold voltage fine tune, which is not existent to digital. Apart from that, analog MOSFET is having other provisions so that mismatch as well as process variation is taken care. So that uh, if I'm using the digital CMOS process for designing operational amplifier, you'll get the better gain, but at the cost of some process and mismatch variation. Uh, so that if that application agrees for that, then it is not a problem. But generally, it does not agree. So that people go with the uh, in digital CMOS process. Along with that, people go with the analog CMOS process, which we call it as a mixed mode CMOS ICs. And and as the technology reduces, you can see that it is really a challenging task to design a high gain operational amplifier, right? And in 32 nanometer, the intrinsic gain of MOSFET is lying somewhere between the 3 to 4, right? Which is really very bad. At least in a 65 nanometer, you are getting around 25, right? So from that, you can say that yes, it is challenging to design a operational amplifier as a lower technology node to have a high with the high gain, and high gain comes with the benefit of accuracy, right? Now this is the IDVGS characteristics. Uh, if you see that three colors there, one is a red, second one is a black, and third one is a blue, right? And top graph, you can say that IDVGS. Red is nothing but a weak inversion, black is nothing but a strong inversion, and blue is nothing but a velocity saturation, right? And as this workshop is having general dealing with the high frequency circuits, you can say, then we are uh, much more concerned about what is happening at the intersection of black and blue, right? Uh, and generally in MOSFET designing, we'll use the region of a SI, right? That is strong inversion region, and that equation is nothing but IDS is equal to mu n CXW by L, which is minus VT square. So it is having some square relation, and weak inversion it has exponential relation. And what about VS? VS is nothing but a linear, right? Because it is not having it is directly depending upon the VD set value of the operational amplifier, right? Means VG, if I'm increasing the VGS, my IDS increases linearly with that, right? And if you see the bottom graph, it creates a concern for a designer because GM, particularly in a blue, you can see that it is constant, right? What it means is that if I wanted to increase the GM of a transistor, even though I am increasing my gate source voltage or VGS, uh, I'll get the constant GM, right? So that how much current I pump into the transistor, or how much VGS, if I increase that VGS, still my GM will be saturated. So that this is really a problematic situation because GM is again related to frequency as well as related to gain, right? So that it is one of the problematic scenario where people are fighting nowadays, right? And this is getting severe and severe further because as the technology node reduces, your uh, strong inversion area is getting reduced further and further, so that you are, if you take the derivation of ID by VGS, it is again your GM will further reduce. Means what we can conclude out of these three slides are, as the moment I am increasing the reducing the technology node, my GM will start reducing. And even though if I wanted to increase the VGS to increase the GM, it is not possible because it is limited by the technology node itself. or fundamentally it is reduced, so that GM is a constant value even though if I'm increasing the VG. So that it is really a tough task to break this scenario. Right now, I think you got the depth of the problem, that technology node reduces even though if I'm increasing the VGS, my GM is a constant because we have reached the velocity saturation region. Right. Okay. Then CMOS technologies versus op-amp. And this slide will give you whatever we have discussed just few slides before. If I'm working on a 65 nanometer, my VE, that is early voltage, is 5 volt per micrometer. VGS minus VT I have chosen as a 0.2 volt. And if we plug these values into gain equation, that is GM into RDS, it is nothing but 3.2, which we are talking about previously. It will, your intrinsic gain of the operation, MOSFET will lie in between somewhere 2 to 4, and 65 nanometer, we can say that it is lying around 3.2. And in that slide, it is a little bit higher, but I think this 65 nanometer, I might have made a mistake, it might be a 32 nanometer, but yeah, AV is 3.2, where from this, we can say that, yes, it is really a problem because intrinsic gain itself is small, right? And even though if I'm trying to increase my V in, right, my GM is limited. Means here you can see that double whammy is that even though if I wanted to increase, I cannot increase. I am limited with the smaller intrinsic gain, right? Then how to tackle this kind of issues? Then as CMOS technology node reduces, op-amp gain reduces significantly, and this is a problem with the designing an accurate circuit. In previous circuit, if I say this, yeah, in the intersection of red and red and black, that is when I'm starting the strong inversion, right? There also people are designing a lot of sensor circuit, sensor-based front-end circuit, uh, right? Because generally people are very much worried about the very much worried about the power. Power consumption, right? Means in that designing like handheld equipment like a mobile or some biomedical applications, so that when people wanted to send something and amplify something, generally people work or designer work into that particular region where red and black intersects, so that so that uh, uh, so that you will get the higher, means actually we are working on a weak inversion, right? So that you have to increase your W by L such a way that you are operating at the below ETH, right? But again, as it is having its own problem because it works with the dependency of exponential with the current, right? So that they're having their own problems, and at the higher frequency designer, they're having their own problems. Then how to deal with this? How to increase the open loop gain? First one, that is idea one. At the black, we have studied that loop GM into RDS is very, very small. That is nothing but 3.2 we got, right? Which is very, very less. Then how to increase that? It is, everybody knows that we can use some cascode at the low frequency, right? We'll cascode so that at the high gain we can get at the lower frequency, where again your dominant pole will be shifting at the lower frequency, that we can see, or that 3 dB bandwidth has been reduced in a red hat as compared to the black hat, right? And gain bandwidth is again GM1 into CL, right? In both the circuits, your unity gain bandwidth is exactly same, right? So that this is one of the idea where you can increase your open loop gain. What is the next idea? Next idea is gain boosting technique, and here you can see that here you will get the amplified version of V in, right? And if I increase this V in, I'll reduce this drain of M1, and I'll increase the gate of the M2, right? And uh, one second. Yeah, this is nothing but a gain boosting circuit, right? And here you will get the gain in terms of a GM1 RDS1 into GM2 RDS2 into GM3 RDS3, right? So that all these three blocks will get added. And but again, at the end of the day, gain bandwidth is again bandwidth, unity gain bandwidth is again GM1 by CL. This is also one of the technique people are using, but uh, uh, but but always you have to make sure that swings of the operational amplifiers, right? Means sometimes it may happen that one of the transistor gets into the linear region, so that so that your so that it creates a non-linearity at the output, right? This is idea 2. What is the idea 3? Idea 3 is uh, quite nice, because we are having, if we forget the M2 transistor, it is nothing but a comparator, right? It is having M3 transistor will give the positive feedback, and general positive feedback is very, very high. And if we see the AV equation is nothing but GM1 divided by GM2 into GM3. And if if you see 2 and 3 transistor, means all top 4 transistor at the bottom, VGS is same, VDS is same. If I make idea, if I make W's or areas also same, then everything is same for them. So that matching the GMs is very, very easy. So principally speaking, you should get the open loop gain infinity, right? Because GM2 and GM3 is close to 0, so that AV should be infinity. But again, it is having its own concern that it's very difficult to match GM2 and GM3. Apart from that, it is having the issue with the positive feedback, right? As the comparator is having the positive feedback, then again, similar kind of issues you can find it in this configuration. But at least we know that how to increase the open loop gain of a amplifier. At first instance, if I'm using this configuration at independently, then it works very fine. But the moment I'm connecting into the closed loop, it may create a problem, because it is having its own positive feedback inside the circuit. So that this is the concerning part. So that you can see this circuit is not quite frequently used uh, into the publication as well as in the industry. Uh, Before going ahead, in industry, generally people go with the simplest kind of solutions, because in industry, workability of the product workability is much more important than designing with some fancy ideas, right? Even though your performance is increased by quite a factor of amount, right? So that in industry they work with a different mindset, and in university we work with a different mindset, right? because uh, 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 because in our case we are like, we wanted to publish something new and uh, new and innovative, which improves the performance. But in industry they should work to work the product, to deliver a product, right? and and performance is even though it matters a lot, but it is not at the cost of failure of the chips, right? So that unless and until it is very well tested and proven, industry is a little bit skeptical to accept the newer ideas. Okay, then this is idea 4, and idea 4 is nothing but a bootstrap idea. It is quite an old idea, but still it is quite interesting. If I increase the V in, right, I'll get some increment at the some Vx voltage at Q2. At Vx voltage, I'll get the emitter of a Q2. This is just uh, bootstrapping of that voltage, right? So Q3 also will get the Vx, right? Means Q1 is having Vx, Q1 emitter is, sorry, collector is having Vx, and Q3 emitter is having the Vx, right? Have you got the idea? Means whatever collector, Q1 collector is having similar voltage Q3 emitter is having, right? So that principally no current is flowing from R3. That means R, that means R is infinite, right? So that this is very nice circuit technique by which I can increase the value of resistance to the infinity so that you can get the GM into RDS very, very high, GM into R very, very high, right? This idea is uh, also very beautiful so that people can work with bootstrapping, and people are using bootstrapping technique to increasing the gain, right? I think you got this because principally speaking, what I wanted to say is that whatever voltage at the collector of Q1, it is exactly similar emitter of Q3, right? So that R is principally infinite, so that you will get the very high gain. And this is idea 5. In idea 5, what we are doing is that we are just cascading the circuit, right? If I'll get some amount of gain from a first block or first stage, then I'll connect next stage or second stage to that, so that overall gain will be GM1 into R1 into GM2 into R2, and further, the moment I started cascading the things, I'll get huge gain at the end, right? But I cannot go like this infinitely because every node it's having its own capacitances, right? And and because of that, there will be the issue of the stability. So that what generally designers do is that they can go till 2 stage is very, very common. They can go to 3 stage, which is not very common, and 4 stage, it is really when it is needed. Generally 4 stage is avoided because 4 stage amplifier is avoided because it is uh, it creates a lot of stability issues if we don't stabilize it with the proper measures. And for making for adjusting the stability of 4 stage, you have to consume a lot of power and area, so that generally people don't prefer 4 stage amplifier. 3 stage also is little rare, but definitely 2 stages is uh, it's very common, right? So that before going ahead, uh, I would like to ask as the people, those who wanted to ask any queries or concerns.
Hello, sir.
Okay. Yeah, please go ahead.
Sir, in one of the slides you talked about analog MOSFET and digital MOSFET. So what is that
Right.
exactly?
Oh, okay. It is called as a mixed mode process. Generally, there are three kind of process in the industry. With the thumb rule, we can say one is a digital process, second is the analog process, and third one is analog or RF process, and third one is a mixed mode process. In digital process, generally in fabrication, if you know the symbol of that particular MOS, if you take two MOSFET, if you wanted to see visually in your cadence tool, you can segregate the layers of that MOSFET. You will find that there are some few more layers exist with the analog MOSFET, which is not exist with the digital MOSFET, right? And why it is? Because in a digital MOSFET, it is streamed such a way that it is having the threshold voltage lesser, so that it is having the higher GM, right? Because in digital domain, we don't care about the mismatch and mismatch and other variations. Process also people don't care much because it varies. All transistor goes into similar process or similar kind of thing, right? So that in digital process, we don't cure we can say, don't cure the threshold voltage or optimize the threshold voltage so significantly, which we needed into the analog MOSFET, right? Because in analog process, also we have to consider that it should give the adequate performance not only in terms of a speed, but also in terms of a process and mismatch, right? So that it for doing that, it is necessary that you have to increase your threshold voltage a little more as compared to a digital MOSFET, and in that process, in that step, the moment you started increasing your threshold voltage for analog MOSFET, you will start reducing your GM, right? And the moment your GM has reduced compared to your digital counterpart, you will get the uh, lesser output gain. Is it okay?
Sir, can you please
Okay, sir.
elaborate this
Yes.
point again?
Okay.
Can you please elaborate why BT is to be more for analog MOSFET?
Okay. Yeah. And that circuit, that graph, what I have shown here is that as a technology node, particularly in 32 nanometer technology, digital MOSFET or digital MOSFET, I'll say now, digital MOSFET shows the higher intrinsic gain compared to the analog MOSFET, right? In digital MOSFET, we don't we means generally in process designer will not care much about your threshold voltage variations much, so that your threshold voltage will not be cure much, because if suppose for example, if in digital MOSFET, if I'm using threshold is 200 through a 200 millivolt, then it's fine, right? We don't have to cure much, because
Okay.
for smaller VTH I can pump larger amount of GM, right? And digital is principally is designed for that, right? Means I can pump larger amount of current so that I can get a larger amount of speed, right? But in analog domain, right? In analog CMOS process, you are having little bit more mass as compared to a digital process. And because of this more mass, what generally people are doing in that is that they can cure their threshold voltage more compared to a digital MOSFET. And while curing that, you will get the larger amount of threshold voltage compared to a digital MOSFET. Means it is not largely 200 to 300. It may change from a 200 to 250, right? And because of this overdrive change, you will get the lesser amount of GM which you are able to get into a digital process. And as GM has reduced into analog process, you can get that lesser amount of gain. Is it okay?
Hello,
Yes, sir. Thank
hello,
you.
sir.
Yeah,
Hello,
yeah,
sir.
please.
Sir,
Yeah.
sir, can you tell me what is the typical values of threshold voltages for 32 nanometer and 65 nanometer?
uh, it varies with the process, because 32 I have recently worked on a 65. uh, uh, Typical values, right? You're asking. Typical values should
Yes, sir, typical.
must lie between 400 to 500 millivolt. I mean, I have worked on a 65 and 32. Both are having around 400 to 500 millivolt. But again, it varies, right? As you
Okay.
increase the channel length, it will reduce a little, right? So that it is, I cannot say that okay, this is the value of 400. I can give the band. It can vary from 350 to 500. At the moment you started increasing the channel length, your threshold voltage reduces a bit.
Okay. Sir, and the supply voltage will be 1 volt for these two technologies.
Yeah, 1 volt.
So it cannot go beyond 1, right?
It is it till now I am not aware what is happening with the 12 nanometer and 7 nanometer, because I have worked with 16 nanometer, and there I have used the VDD of 1.1 volt.
1.1 volt. Okay.
Yeah.
So means can we design a means circuit with 1.8 supply volt at this technology 65 or 32? 1.8 volt.
1.8 volt, it is possible, but you have to use
Okay.
the different kind of transistors. There are generally in every process you will be having the nominal VT transistor, high VT transistor and low VT transistor. If you wanted to design for 1.8 volt with the technology node lower than suppose 65 nanometer, for example, where I'm working with the 1.1 volt nominal VT transistor, I can use HVT transistor or high VT transistor to design at 1.8 volt.
Okay, sir.
Okay, and high VT transistor generally what your threshold voltage is higher compared to, means you can go around 700 millivolt or something like that. Right.
Okay, sir. Thank you, sir.
Okay, and generally those high VT transistor people are used for IO transistors or IO pads only, right? Because why this provision is given is if I'm having suppose a power amplifier IC which works on a higher voltages, then these two ICs you can add into the similar SOCs as similar SOC itself, right? Without any voltage shifting method. Are you getting what I'm saying? What I mean to say is that if I'm having some circuit which works at 1.1 volt and another technology, suppose another chip we can say, which works on 180 nanometer, which works on 1.8 volt. And if you are to combine this, then while combining, you can use the high VT transistor, which works on a 1.8 volt, so that you don't have to worry about the level shifting and all. Just you can use the high VT transistor and combine these two circuits.
Yes, sir. Understood.
Right?
Yes.
If I have to drive generally in many circuits, people use level shifters because the external IC generally works at the 5 volt, like communication ICs particularly. I don't remember the name exactly, but yeah, other communication ICs which works on particular digital ICs, they can work on a 5 volt nowadays, so that when I am working, I work on as 1.1 volt, and I'll use the level shifter so that I can drive the 5 volt IC at the out.
Hello, sir.
Yeah, please.
Sir, in one of the slide you said that for 65 nanometer we can get the gain of around 25 intrinsic gain.
Yeah.
So for 65 we can get 25, or is it 3 to 2 to 3?
Yeah, actually that I made a mistake in the latter slide. Actually in 65 you can get the enough gain around 20-25, but at the lower 32 nanometer it will reduce significantly.
Okay, so at 32 it will be 2 to 3, no? Means range will be 2 to 3.
Yeah. 2 to 4 around, yeah.
2 to 4.
Intrinsic
Okay.
gain I'm talking about. You
Intrinsic
can
gain.
increase that later.
Okay, and at 65 nanometer we can get at 25.
Yeah, around
25.
Yeah. This is just a thumb rule. It changes with the technology to technology, but yeah, you can get approximately those numbers.
Okay, sir.
Yes, Purnima, I think you wanted to ask something, I guess. Dr. Naveen, how much time I'm having now for this session?
We have time till 1 o'clock, half an hour more. 30 minutes more.
Okay, then I'll move to the presentation.
Hello, sir.
Yeah, please.
Nowadays, the people are using the 0.25 volt, 0.3 volt also for the 180 nanometer technology. Is it possible, sir?
I'll come to those points in the next few slides. But again, as you asked the question, I would like to elaborate here itself, is that generally for presenting the paper generally people will say that, okay, they can operate at the 0.5 volt, or I have not seen 0.3 volt, but yeah, 0.5 volt at the 180 nanometer technology. And they claim that they can save the lot of power by using that. But again, they can show that it is working, but as I said, analog IC design you cannot get freely. Then so that if you read those papers carefully, you will find that somewhere that performance in terms of a noise or mismatch or process, it might be having some other issues that author might have mentioned or might have not mentioned. So that even though, yes, means you can implement it and claim that you have reduced the power, but at the same time, you have to be a little bit skeptical what other parameters is missed out of because of that.
Or sir, is it
In
the hello?
Yeah,
Sir,
yeah, yeah.
is it the case
Dipesh.
with that digitals are working at lower supply voltage, so analog trends is also towards the lower supply voltage? Is it the trend, sir?
Yeah. Means it is called as SOC. Generally, people are using means silicon on chip, where mixed mode process is quite prominent nowadays. Whether you go for a RF application or a sensor-based application, right? So that yes, analog and digital works on a similar wafer itself, right?
Oh, thank you, thank you.
Yeah. Anybody else? Okay, then I'll move to the presentation. Here we'll go a little bit deeper, where, sorry. Yeah, speed, noise, and power. And before going ahead, I'll go with the quick revision. This is nothing but a single stage amplifier, right? Once I'm having only single differential pair, that is classic 5 transistor differential pair, and load capacitance CL is connected, so that you can get the gain bandwidth is GML by CL, right? And that is also visible by this, where if second term is quite prominent at the frequency increases of a denominator second term, then that RL is getting cancelled in GML by CL, which is a gain bandwidth. And at the low frequency, how much gain you will get is S is equal to 0, so that GML into RL. This circuit is very basic, right? Then if I wanted to increase the gain, then what I can do is that I can do some cascading and connect some capacitor in between output of first and output of second, which we can call it as a Miller capacitance or stability capacitor, right? And if I solve the equation, I'll get the DC gain is GM1 multiplication of both the GMs and multiplication of both the output impedances of two stages, right? But apart from that, I'll get the two poles, right? One is a dominant pole, which is getting created because of the CM, and another non-dominant pole, which is GML by CL, which I can call it as a first non-dominant pole. But unfortunately, we'll get another term that is in a numerator. We can see over that in a bracket is 1 minus SCM divided by GML, right? Means it is nothing but a RHP0, and RHP0 is considered to be very bad, right? It is bad in all sense. It reduces the gain, it reduces the phase, so that RHP0 is always people would like to avoid, right? And here again, same thing which I have talked about. This is minus 3 dB is nothing but GML R0 and RL into CM, right? And P2 is GML by CL, that is the first dominant pole, and 0 is nothing but GM2 by or GML by CM, right? And this is the response which frequency response which you can get over here is that generally Z1 can come at the come before the P2, and this is generally not at all what you can say permissible, because as it is a LHP0, your phase response reduces by 90 degree, means asymptotically 90 degree, and P2 comes immediately after that, so that at that particular frequency you are having the double factor which reduces your phase margin significantly, right? So that what we can do is that either somehow compensate that zero, that LHP0 should be compensated by the RHP0, right, or a pole, right? Or I can nullify that zero at all, right? So that what we can do over here is that, right? Then how to select the value of CL, right? CM, right? Because CL is already given by for the designer. Then you can select the value of CM by this equation, generally gain bandwidth is generally set to half to obtain a good phase margin, right? Means something your GML by CL, that is P2 should be 2 times larger than the UGB, that is GM1 and CM. And from this equation, we get the value of CM. What CM value or Miller capacitance you need to connect, right? But again, Z1 will create a problem, right? From this equation, again, you will get, okay, what from here, from this equation, you will find the value of CM. But again, what kind of relation you require for GM and GM1 divided by GML, right? Means what transconductance you have to select, that is also one of the important factor, right? So that how to select those values, that is also one of the important thing. Means here I have selected the this equation gives me how to select the value of CM, but at the same time, how to get the value of GM1 by GML, that is also one of the concern, and this plot will give the answer for that. And this is the equation of phase margin, that is 180 degree minus tan inverse of gain bandwidth divided by dominant pole minus gain bandwidth divided by first non-dominant pole and minus tan inverse of gain bandwidth divided by LHP, or sorry, RHP0. And this equation you can see directly is that 180 degree minus tan inverse of GBW divided by dominant pole, which will give around 90 degree, right? So that 180 degree minus 90 degree minus tan inverse of GBW divided by P2, it is nothing but half. As I said that your P2 should be double the frequency than GBW. So that this will give around 27 degree, right? So that 180 degree minus 90 degree minus 27 degree will come as a 63 degree, right? Then what is the phase margin is nothing but 63 degree minus tan inverse of GM1 by GML. And from here you can figure it out what is the value of GM1 and GML required, right? If GM1 and GML is 1, right, ratio is 1, then your phase margin is very, very poor. And if it is infinity, then your phase margin is 63 degree, right? If it is a 0, tan inverse of 0, right? Or very, very small. That means what we can gauge from this is, if we can put into the sentence is that my GML value should be very, very large than the GM1 value, right? So that I'll get the better phase margin. Okay, then what it means is that your second stage GM should be very, very large compared to the first stage, right? And if I wanted a second stage GM should be very, very large, then I have to pump larger amount of current into the second stage, right? So that at the end we can conclude over here is that if I wanted a higher GM, I have to pump larger amount of current, I have to pump larger amount of power, so that I'll get the phase margin better, right? Means for getting the better phase margin, you have to burn power, right? So that again, same thing, nothing comes for free. For getting the better phase margin, you have to have more power. Again, this circuit itself is having different connotations, but at this moment, we'll stick to this, is that if I wanted to get a better phase margin, I have to sacrifice the power, right? Apart from that, as I said, 0 is always a problematic, particularly RHP 0. Then how to nullify this? Then just I have to connect the one resistance over here. Actually, physically, what is happening is that at the higher frequency, if I'm not connecting the RM over there, or circuit is something like this, at the high frequency, what is happening? Your capacitor is conducting, so that as the capacitor is conducting, it is pumping, it is having direct path actually from V into out, right? Means if there is a direct path, we can say that it is a 0 is coming, right? Then how to avoid the direct path? Create some resistance, right? So that I have connected the RM over there. This is a simple understanding. If I wanted to create some resistance, I put the resistor, right? And after solving this equation, I'll get the everything is same, like a P1, P2, gain bandwidth, low frequency gain, everything is same, but I'll get the 0 equation, which is quite interesting. It is 1 by Cm into Rm minus 1 upon GML. And here I am having the freedom to select the value of Rm. If I select the value of Rm exactly equal to 1 upon GML, that is the second stage gains transconductance, then this 0 itself is getting cancelled, right? So that what I can get here is that you can see there's a red graph which I have corrected, a red a line which I have corrected is that you will not get the 0 straight line. Instead of that, I'll get the minus 20 dB is getting continued till P2, and after that it will start falling, right? What is the advantage of this is that previously my phase margin is degrading at the 0 as well as P2, but now my phase margin has been improved so that I can so that I have benefited with this. But more advantageous is that as 0 is previously 0 was here, right? So that my unity gain bandwidth was a little bit limited because of the 0, so that I can push my UGB further, right? These are some tricks people do to improve the gain bandwidth product. There are some other things people do. If I don't want it to resist, I don't want it to use the resistor, I can pump the current from externally as well, right? What it means is that when zero is coming, because current at the high frequency CM is conducting and it started pumping the current into this. If somehow whatever current is getting pumped onto the output node, it is getting sucked by another some circuit mechanism, that 0 is not valid, right? Are you getting what I'm saying? Why 0 is coming? Because capacitor is pumping some current. If similar amount of current, if I'm able to suck from that particular node, then it is something like that. There is no current exists into that particular node. Similar thing is happening over here. Previously, by putting the resistor, we are creating the resistance for that forward current. But here we are allowing that forward current, but we are compensating from other circuit technique, right? Similar thing means conceptually both are same, but conceptually outcome is same, but conceptually both are different, right? One is resisting and one is allowing, but compensating later on, right? And it is also, we can see over here is that AV1 transconductance of AV1 and transconductance of AVF1. If we are able to make it equal, then I can cancel the 0 at all, right? And this is very much achievable because whatever differential pair you are using to design AV1, similar differential pair you can use it for a AVF1, so that you don't have to worry much about that, right? And even though there is a process and mismatch variation, these zeros will push at the very, very high frequency, so you don't have to bother at all about that as well. So that these circuits are work fine. In the resistor, problem is the process variation, right? The process variation here, because of that, resistor shows a lot of process variation compared to the transistor and capacitor, so that whatever compensation scheme you have implemented, you have to be very much sure by running all the corner and mismatch analysis before proceeding with that, right? So that at the end you will make sure that it works. But as something is compensating, something I have to compensate for a similar kind of a quantity, means I have to compensate for a MOSFET with the MOSFET, then it is not a problem, right? So that similar thing is happening, and this is also quite popular method, which we call it as a feed forward compensation, right? Now we'll quickly go through what is noise. Noise is also one of the important parameter which generally people consider while designing a operational amplifier. There are two kind of noise which I have discussed before, or which I have just named before. One is a thermal and second one is a flicker. Flicker noise is very much important when I'm designing a circuit for a sensor applications, and thermal noise is generally when we are using for data converter, high-speed data converters, as well as RF circuits, right? And Interestingly, if we look at over here, is that if thermal noise, if I wanted to increase, I have to increase the reduce, then I have to increase the GM, right? That means, and at the end, I have to increase 1 by W by L, means I have to increase the size of a transistor, right? And 1 by F noise, this KFF is nothing but a constant, right? Then if I wanted to increase, reduce the flicker noise, I have to increase the area of a transistor, right? There is some subtle difference. Why at first case I have to increase the size of a transistor. Here I have to increase the area of a transistor. It is having similar kind of connotations, but it may be different, right? Means at the end, what I have to do, I have to increase the area to tackle with the tackle with the noises, or I have to increase the GM by pumping the extra current, or I have to sacrifice the swing to get the larger value of GM, right? And there are a lot of permutations and combinations for a designer. Depending upon the which application you are designing a circuit, you have to figure it out or choose one, right? So that now it is very much clear that if I wanted to increase the noise, I have to reduce the noise, I have to increase the area or power or sacrifice on a swing. There are certain things people are using, which we call it as a bulk biasing, which is very much popular nowadays, but unfortunately it is having its own problem. One problem which is quite evident is a noise. Here, if I wanted to model the thermal noise, if I'm driving the bulk transistor or considering the bulk driven transistor, then here you can see that GMB is coming into the denominator, and GMB value is around 3 times smaller than the GM of that transistor, right? So that if I'm using the bulk driven transistor for designing my operational amplifier, it definitely it is noisier than gate driven transistor. And whatever it is true for a thermal, it is true for a flicker as well, right? So why bulk driven people are going nowadays? Few people are going in nowadays, not all. Generally for publication people go, not for actual purpose. I have not seen any actual circuit designing with this bulk driven, because it's having not only noise, it is having some other issues as well, right? But we now concentrate on the noise. Is that bulk driven? Yeah, bulk driven, why people are going, because it says that if I'm going with the bulk driven, I can bias the bulk such a way that bulk and source junction is forward bias, and you can reduce the threshold voltage of that particular transistor, and you can operate at the lower VT. Okay? This is one of the catching points, so that people started working on a bulk driven transistor, right? But yeah, definitely it is noisier than gate driven. So next time onwards, if you wanted to design a circuit or if you wanted to review the paper, just keep this in mind, right? Then whatever noise you can get with a single transistor, if I put into the cascode transistor surprisingly doesn't give any noise. So that it's very, very, unless and until you are very much worried about the swing, you can go with the cascode configuration, because you get the free gain out of no noise, right? So that sometimes circuit do the miracle. This is one of that. Cascode is one of that, because you are getting something on a sacrificing very little. Okay, then yeah, generally, personally, I like the cascode kind of architectures. This is again a gain boosting. You can increase your gain further and further with the no noise penalty at all. So that this is also one kind of circuit which is kind of favorite to many designers. If you are not very much, if you take care of the swings at every node, so that transistor will not get into a linear region, this circuit does the miracle, because it increases the low frequency gain as well as at the no cost of noise penalty, right? Yeah, this is also one of the important slide which I wanted to discuss. AVT. AVT is nothing but a coefficient of a threshold voltage, and generally it is provided by the every foundry, right? And for 500 nanometer, the value was AVT is around 10 millivolt per micrometer, right? And AVT is exactly, or it is having some relation, direct relation with the spread of threshold voltage, right? And we want lesser and lesser spread of the threshold voltage over the process, right? And if we look at carefully, the AVTH or AVT is reduces with the TOX or oxide thickness, or reduces with the L, right? As your channel length is reducing, oxide thickness is reducing, your AVTH is also reducing. So that at the lower technology node, you can say that your spread of the threshold voltage is very, very small. And generally it is true also, right? But unfortunately, it is only true till 13 nanometer, right? Why it is? Because after 13 nanometer, you have reached a physical boundary. You have reached a physical boundary of the MOSFET, because thereafter AVT is almost getting saturated, and it is governed by the it is limited by the roughness of the MOSFET edges, so that it's barely we can do anything, or foundry can do anything to reduce the AVT further, so that it has reached its physical limit at this point, right? So that AVT, if you wanted to have something in 1.2 or 1.3 at the lower technology, it is not possible, because we always AVT is stuck to the 2.5, right? So that it's if mismatch is very much concerned for sensor applications which is operating at the very, very lower technology node, generally it does not happen. It is this graph is really a nightmare for them. Right, before going ahead, I think only 5 minutes are left. I'll ask Dr. Naveen if
Yes.
yeah, you can ask the audience. Means I am also asking the audience, if anybody is having the questions or doubts till now, they can
Ye-
raise the concern.
Yeah, if there are any questions, I think there are a few questions in the chat box, but I guess those are all been discussed and answered.
Okay.
Hello, sir. Hello.
Yeah, please.
So what is this AVT?
Oh,
You just
AVT is,
discussed.
yeah, AVT is the coefficient, mismatch coefficient, threshold voltage mismatch coefficient provided by the every foundry, right? Means if 180 nanometer, it provides some number. From that, you can get the rough guess that how, if I'm fabricating my transistor, how much threshold voltage variation I can get after getting it fabricated, right? Are you getting? It means foundry has given some information to the designer, or some window of the designer. Your threshold voltage varies by this much amount if your area is this much, right?
Okay, sir.
Right, means it is something like a reference point given by the foundry beforehand to the designer, so that he can or she can design the circuit by keeping those into the mind. Yeah, this much threshold variation I can get after getting fabricated.
So then what happens with this AVT if we are going for the reducing technology node?
Okay, if generally thumb rule is that if I wanted AVT, we cannot do anything. But again overall, if you see the equation, right? Yeah, I cannot do much with the AVT, but always I can do with area. So that what I can do is that I can increase my area such a way that I can reduce the spread, right? Means at the end, what I wanted, I have to reduce the spread of the threshold voltage, or sigma of the threshold voltage variations, right? So that, I can do it another way by increasing the W by, right? But problem of the area increment, again, you will reduce the speed and all.
Okay.
But yeah,
So,
generally in sensor based application, we don't care that much about the speed, so that If I wanted to design the circuit for sensors, then definitely I can increase the area. Yeah, please go ahead. Yeah. Yes, Miss Madhuri, I think you're asking something.
Madhuri, do you have a follow-up question?
Yes, sir. Sir, that one of the slide you showed, that RC compensation, operational
Yeah,
amplifier.
RC compensation, right? Yeah.
So I have one question. So if we are using that RC compensation technique, so we can improve the phase margin. So what can be the maximum phase margin we can go till if we are
Oh,
using
okay.
130 nanometer technology node, 130 nanometer?
I think it does not have anything to do with the technology node. Here it is, again, you can see over here, this graph tells you the story. Maximum phase margin we can get is a 90-degree, right? Because you will always have one dominant pole. But if you wanted to sacrifice more and more power, then you can go above 63, a bit in between 63 to 90 degree, right?
Okay.
What your question? How much minimum phase margin you can go, or
No,
how
no,
much
no, sir.
maximum phase margin?
Means if we are using RC compensation, then what can be the maximum phase margin achieved? Means
RC
in degrees.
compensation.
Normally we are saying 60-degree phase margin is enough. Means 60-degree phase margin is enough for the stability of op-amp.
Hmm.
So can we get more than 60-degree phase margin? Is it possible with the technology?
Yeah, it is possible in any technology, right? It is just you have to make sure that your non-dominant pole, which is at the
Okay.
very, very high frequency than UGB, right?
Okay. Because
Because we
sir,
are compensating. Yeah,
okay.
please.
So
Go
actually,
ahead.
why I'm asking this doubt, because I have simulated one circuit, that is CMOS operational amplifier, two-stage CMOS with RC compensation with Sky 130 technology node, Skywater
Mhm.
130 nanometer node. So in that, I got 200 around 200-degree phase margin. So just I want to confirm whether is it possible or not. It's in
No.
simulation I have got it.
I think I personally think that it is not possible. I think you might have uh, miscalculation or interpreted the results. I believe that,
Okay.
but
Okay.
yeah, maximum you can get up till 90 degree, right?
90-degree.
And and minimum
Okay.
it is lesser than that, right? It can go to zero once you're completely unstable,
Okay. Okay, sir.
right?
Thank you, sir.
Yeah. Anybody else?
Are there any other questions from the participants? Yeah, if not, I think we can break here for lunch and we'll return after at 2 o'clock for the next session. Is that
Okay.
fine?
A
Okay,
1 hour
sir.
break or half an hour break?
We have 1 hour. 1 hour. It's 1
Oh,
o'clock in India here. 2 o'clock we'll resume.
okay. I'll do
Okay,
that.
sir.
Okay, then after coming back, we'll see. 1 second. I'll just give a review. Comparison of some few architectures of operational amplifiers, right? And we'll try to compare with some unique number, that is figure of merit, right? And we'll try to compare all the architectures with the figure of merit and what are the current architectures which can get the very high figure of merit. So that after 1 hour, I think we'll switch to that. Okay.
Okay. Okay. Thanks,
Thank
Dr.
you.
Vinayak, and all the
Yeah, thank you,
participants.
Doctor.
So we will break now and we'll come back at 2 o'clock with the same link. Okay.
Yes, sir.
Thank you.
Okay, sir. Thank you.
Okay. Thank you.
Okay, thank you. Bye.